Welcome. This talk is about diffraction and reflection of antiplane shear waves in a cracked microstructure material, and this is a joint work with Professor Enrico Radi and Professor Mishuris of Aberystwyth University in UK. And this talk is delivered on occasion of the Crack Path conference from 21st to 24th September 2021. So let me first introduce you the table of contents of this talk, and first of all I shall give a little bit of motivation. Why are we interested in this analysis? I shall discuss very briefly about elastic waves in classical and microstructure materials. Then I shall introduce the problem and its governing equation, and finally we shall reach a solution in the time domain, and then I'll draw some conclusion and acknowledge the findings. So let's start with the motivation. Why are we interested in this problem, and what is the problem we are interested in? So first of all, let me tell you what the wave diffraction is. Diffraction is has long attracted major attention since its discovery in the 17th century by an Italian scientist, Francesco Maria Grimaldi, in the context of light rays diffraction. And diffraction is really any time a ray changes its path, its direction. And this may be caused for whatever reason. And we have special kind of diffraction like reflection, or for instance, you have refraction. These are special kind of diffraction, so they all go under the name of diffraction. So diffraction is a very useful phenomenon because it can give you a very important insight into what occurs in the mechanics of the ray propagation, of the wave scattering and propagation. But then diffraction has a very important role when it comes to cracks. So when people usually think about cracks, they think about elastostatic problems, for instance cracking elastic materials. But really also cracking is a dynamic process. And there's a lot of influence of the dynamic contribution into the whole process. For instance, if you look at the picture, this is an experimental picture and gives you an idea of what happens to surface waves or Rayleigh waves when they encounter a crack. And this is the foundation of the reason why we use, for instance, localized surface waves in non-destructive testing when we want to determine whether there are some defects in the materials. So only fairly recently people would understand the importance of dynamic effects in determining the stress concentration in the presence of geometric discontinuity. In fact, dynamic stress concentration is a result of the diffraction of elastic waves. So when you think about stress concentration, you think of it in statical terms, but really if you enlarge your viewpoint in a dynamical sense, you will find that the stress concentration is much bigger and more diverse than you would expect. So there's a very important effect of diffraction in the stress concentration phenomenon. And then of course you have another important factor to consider when you consider crack problems, and that is the microstructure. So materials may appear homogeneous and isotropic at the large scale, at the mesoscale, but if you look at the microscale, there is a microstructure, so materials are never homogeneous. And this plays a very important role, and it's important when you're looking at the stress concentration in the neighborhood of the crack tip, because there is where the microstructure comes into place. So then, we can consider microstructure in a lot of ways. There's a lot of ways you can do that. For instance, people that consider propagation of cracks really go to the level to the micro level of incorporating for instance, the interfaces between the grains in granular matter, for instance. But if you want to do it from a continuum mechanics standpoint, you can still do that and embrace generalized continuum theory. And there are very many of these, and each of these has its own advantages or disadvantages. In this talk, I will consider the presence of the microstructure through the couple stress theory of elasticity. And in the couple stress theory of elasticity, as the name suggests, you have an exchange between two material parts of not only of the traction vector, so the usual Cauchy vector, but you also have a couple stress reduced traction vector. So you have a torque which is exchanged by the two materials. And so the question arises, shall we stick with the classical Cauchy material, or shall we move to generalized continua? Shall we need a more refined theory and more complicated? And this is a very difficult question. People has been trying to address this question for a long time. I cannot give a final answer, of course, but I can suggest that the right approach may be to consider the right theory for the right phenomena you're looking for. So if you're looking for some general phenomena that the classical theory is very well equipped to capture, then you should stick with it. But if you want to move beyond the classical theory, if you are looking at some special effects, then you should move to generalized theory. And for instance, to give you an idea of what this distinction may look like, we can look at advantages and drawbacks of a couple stress theory, for instance, the one that we chose in this particular context. So it's the simplest higher gradient theory. It's a strain gradient material theory, and therefore you have a higher gradient. You need more boundary conditions. It incorporates two internal characteristic lengths, which, and this is important, can be easily determined experimentally. I wouldn't say easily, but they can fairly easily, in the sense that you can try different experiments, like static experiment of bending and torsion at different length scales, and you can look at what happens. And if you do that, you can see that there's a stiffening effect, and this can be represented by an internal characteristic length. Of course, you have a third parameter, which is the microinertia, and this is more tricky also to determine experimentally, but it's a very important parameter. So it accounts for how hard it is to twist, to torque the material microstructure. So if you incorporate for these two features, the model is no longer self-similar, and this gives you a lot of advantages. For instance, you have now dispersive bulk wave and localized, namely Rayleigh waves, which is experimentally correct, and you do not find this in classical theory. And furthermore, an internal length scale allows you to finally determine the dimension of some well-known phenomena, such as shear bands or high stress concentration regions, which you would not be able to see in a self-similar theory, because of course in a self-similar theory there is no internal length scale, so there is no way you can determine the length of something unless you introduce this length scale from externally. For instance, this is the case of love wave, which arise by introducing an external layer. So you introduce a layer structure of the material, and this, of course, given the different thickness of the two layers, introduces a length scale. However, the complete couple stress theory is not objective, so in the presence of rotational inertia. But this problem can be completely eliminated if you restrict yourself to time harmonic motions. Then let's have a very quick look at elastic waves. So elastic waves, as you know very well, are divided into two families. You have longitudinal waves, which are the P waves, or you have shear horizontally polarized wave, which can be either vertically or horizontally polarized waves, SV and SH. They are slower, they are distortional waves, and they come second. And in fact, if you look at the seismogram for earthquakes, you can clearly see these waves taking place. So first you have P waves, primary waves, and then S waves, and then finally you have localized waves, which are the most important part of the seismograms. But then if you look at the full picture, so if you look at all the waves together in all directions, you can appreciate that you have also a phenomenon which is similar to Rayleigh waves this is the north component in the last picture. So in this case, you can clearly see that you have a phenomenon similar to Rayleigh wave, but the classical theory does not predict Rayleigh wave, which are horizontally polarized. And this problem was overcome by Love in 1911 or something like that, because he introduced the layer structure of the Earth. So Love waves only appear if you modify the homogeneous structure of the object. But instead, if you consider couple stress theory, they appear naturally. In fact, in couple stress theory, and this has been only recently realized, you have antiplane Rayleigh waves, so shear horizontally polarized Rayleigh waves, which are not classical. And they are also dispersive, as this picture shows. So let's now go to the problem, and let's now discuss the features of this problem. So we consider a semi-infinite rectilinear crack, which is located here on the negative part of the x1 axis. And you consider a half space, which is located on the negative part of the x3 axis. And then you consider antiplane motion for this crack problem. You also consider a dynamic loading acting on the surface of the crack. So I, of course, designed the crack like this, but it's really a line. So you shouldn't be deceived by this drawing. And the crack faces are loaded by a sinusoidal distribution of stresses, of Cauchy stresses. So then we introduce the classical measure of strain, which is the strain tensor, but you also have the rotation vector, which is related to the macro deformation through the curve. So basically, the rotation vector expresses the average rotation of the principal direction of strain. And then you introduce the gradient of this rotation vector, which is the micro rotation vector. And so now you have two measures of deformation, epsilon, which is the classical measure, and chi, which is the curvature tensor, which is sometimes also named the Reines tensor. And then you split the Cauchy stress tensor, which is no longer symmetric in its symmetric sigma part and skew symmetric tau part. And then you also have, on any smooth surface, you have 5 boundary conditions, because you have 3 conditions on the Cauchy stress, basically, classical, reduce the traction force. But also you have the couple stress, which can only be given in the tangential plane, so in a plane tangential to the surface. So that accounts for only 2 components. So overall you have 5 boundary conditions, which is equation 4. And then you have constitutive equation. This is the classical constitutive equation, sigma for the Lamé constitutive equation, Lamé parameters, G and capital lambda. And here is the couple stress tensor with 2 new constitutive parameters, which is an internal length scale L and a factor eta, which is similar to the Cauchy stress, the Poisson ratio, sorry. When this factor eta equals to 1, you have the so-called reduced couple stress theory, which has found some success because it reduces the number of material parameters to define. But the way that it has been introduced, it postulates an extra balance condition which is physically not found to hold. But nonetheless, we can still find the same result for the reduced couple stress theory, just putting eta equal to 1. So under antiplane deformation, this is the governing equation for homogeneous material for antiplane motion. These 2 terms, of course, the first one disappear if you have no internal length scale and you're left with the classical equation, except for this term, which accounts for the micro inertia, so the inertia by which the microstructure is rotated. Okay, so if you put everything together, you then have, as you can see, you have boundary conditions. So we impose the traction boundary condition on the crack faces. This is important because this allows us, by subtraction, to solve any problem with a crack, whatever the loading is, because you actually use superposition. You consider the problem without the crack, you determine the loading on the crack, and then you use this solution to subtract this loading so that the crack faces are load-free. So by this approach, which is a classical approach, you can solve any problem with any loading, provided that you use the solution for the problem which is without the crack, and then you add this solution of the problem with the crack where only the crack is loaded, and you choose the particular loading which eliminates the load on the crack faces in the first problem. So as you can see, this crack loading only applies for psi1 less than 0, and psi1 we will see in a minute what is xi1, but basically it's the same as x1, only rescaled. And then you have the absence of a couple stress for xi1 less than 0 again. But then for xi1 greater than 0, since this is a skew-symmetric problem, you have the displacement and the couple stress, which is an even derivative basically, are 0. So this accounts for symmetry. So you can solve the problem only for x2 positive, for instance, so for a half space divided by 2 basically, only half of a half space. But then you have a mixed problem because you have conditions that applied on the crack surface and behind the crack tip, and condition that applies on the crack line beyond the crack tip. So this is a typical mixed problem. And then you introduce a reference length, lambda L. So L is the traditional internal length scale, like we mentioned already, and you have a reference time, T. So you scale everything back, and this is a very important step because it allows you to reduce, to greatly reduce. You can introduce xi1, xi2, xi3 as the scaling of your traditional x1, x2, and x3, and this greatly reduces the complexity of the problem. So you introduce time harmonic motions, you get this equation, equation 10, which is a biharmonic PDE for the function W, which is the displacement, and this of course is the time part of the displacement. But then you introduce lambda in the proper way, and if you introduce lambda in a proper way, you can reduce, you can factor out your equation 10 in this way. And this is important because delta is a real number, both are real numbers, but this is a plus sign, and this is really the speed of antiplane bulk waves, so shear horizontally polarized bulk waves. And then you have 1, which is a evanescent bulk wave, which does not exist in classical elasticity. In classical elasticity, basically, this second term would drop out. And this can only be done if you choose a particular value for lambda, which is a convenient scaling factor which we introduced here. So if you do this, the problem is greatly simplified, although still complicated, and you can attempt a solution. You introduce a complex plane with 2 cuts, and the cuts, you orient the branch cuts such as they pass through these branch points, which are delta, as I already mentioned, the speed of the bulk antiplanes bulk waves, and this m1, which is basically I, because this is imaginary axis, and this is the speed of evanescent bulk waves. And you find the Rayleigh function, and so because Rayleigh waves exist, antiplane Rayleigh waves, as opposed to classical elasticity, you can find dispersion curves for Rayleigh waves. And then you can take the full Fourier transform of the governing equation. You can find a solution in the Fourier space accounting for decay at infinity in the direction x2, and so you only have 2 complex value constants, or I should say functions, to be determined. And then of course you move to take the Fourier transform, the plus and minus Fourier transform of the boundary condition. You find an algebraic condition between C1 and C2 through the boundary conditions. And then finally you reach a Wiener-Hopf functional equation of the second kind, because it has a right-hand side. This right-hand side is the loading, the applied load on the crack faces. This is the kernel of the Wiener-Hopf functional equation, and these 2 functions you need to find. These are the conjugate functions in the Wiener-Hopf sense. This is the displacement, and this is the couple stress. Or I should say, I shall correct myself, this is the reduced traction. A reduced traction on the crack faces. Also, this is the displacement on the crack face, and this is the reduced traction, the traction vector, or better, its antiplane counterpart on ahead of the crack tip. And this is the kernel of the Wiener-Hopf functional equation, which is constituted by the Rayleigh function plus this term that accounts for bulk wave speed. So this functional equation can be solved. I shall skip all the details. You can factor the kernel, you apply a decomposition strategy, and you can find the full solution when you anti-transform, so you move from the Fourier space to the classical space. And you find the displacement, and the displacement is constituted by a few parts which are very relevant. This is a bulk wave part, so you have waves moving like bulk waves. These are waves that are entrained by the applied loading, so the applied loading applied to the surface is causing waves to move in the material. And then you have these two terms, which are terms that are related to resonance. So when you are feeding your loading K, which is the loading wave number, exactly at the value, at the wave number A, you have resonance. And this is resonance because you are feeding exactly at the Rayleigh wave speed, basically. And then similarly, you have a similar phenomenon here, but now this is an evanescent mode. So the A and B are the roots of the kernel function and represent very special waves. And these two waves, this is interesting because this wave, for instance, this wave is classical, or a version of the classical result in mode 1, and this is instead non-classical, and this is related to a quasi-Rayleigh wave, which is characteristic of this material structure. So if you solve the problem, you find precisely that. If you solve numerically the problem, you find that you are applying loading and the load propagates inside. You have the bulk wave that irradiates from the crack. So this is the diffraction really of waves by the crack tip. And this is the special wave, a quasi-Rayleigh wave, which is evanescent, and this propagates orthogonally to the cracks, to the crack. And altogether you have this solution. Okay, finally you can find dynamic stress intensity factor, which, so for the displacement, this is a rigid body motion in the neighborhood of the crack tip, plus the dynamic stress intensity factor for displacement. And this has a very complicated expression, but you can plot it. You've got everything basically by the solution. And the same occurs for stresses, so symmetric part, full stress, and couple stress, and the stress intensity factor, which are all related to the displacement stress intensity factor. And these are some pictures of the stress intensity factor. So I thank you for your attention. I shall also thank the funding by PowerFair 2018, which is expiring next year, and also by the European Union Framework Horizon 2020. In the last RISE call, we got lucky enough to get funded in the project Effect Fact. So thank you very much for your attention. Goodbye.